Hi! When we considered the derivative of a function of one variable, we saw that the concept of the tangent line and linearization both allowed us to start a fruitful application and deeper understanding of the derivative. So it makes sense to try and generalize those concepts also to the setting of several variables. Let us first recall the notion of the tangent line to the graph of a function of a single variable. The tangent line at the point x0 to the function f is the line that touches but does not intersect the graph at the point x0 f of x0. In particular, it is the line going through that point with slope equal to the derivative of f at x0. This leads to the equation for the tangent line you can see on the slide. To generalize this notion to functions of two variables, we immediately have two clear options. Indeed, we could consider the tangent line in the vertical plane parallel to the y-axis and the tangent line in the vertical plane parallel to the x-axis. We saw in the previous lesson that these lines have slope equal to the partial derivative with respect to x and y respectively, and so we find the lines given by the sets of equations shown on the slide. Clearly, such a description with two lines is not quite satisfying, since it ignores all directions that are not parallel to the coordinate axis. Since the graph of a function of two variables is two-dimensional, we would like to find a plane that touches but does not intersect the graph at that point. The formula on the slide is the general way to describe a plane through the point x0, y0, f of x0, y0. The tangent lines are important here since they need to be contained in this tangent plane. In particular, we need an equation of the form on the slide such that any point on either tangent line is also contained in it. Therefore, we obtain the equation as shown on the slide. As expected, its form is similar to the equation for the tangent line in the sense that we find the z value is equal to the function value plus the derivative times the displacement. Except now we have a term coming from the x displacement and separately from the y displacement. Consider the following example. The function is shown on the slide. So we may compute the partial derivatives in the point indicated on the slide to obtain an equation for the tangent plane we see in the picture. Note that the points on the graph stay close to the tangent plane only when we stay in the vicinity of the chosen point. Recall the implications of this last remark in the setting of a function of a single variable. Indeed, we saw that the tangent line was in fact the graph of a function called the linearization of the function f at the point A. This linearization gave rise to the linear approximation to our function and has the property that both the function value and the value of the derivative coincide with those of the function f at the point A. This completely fixes the linearization since it is required to be a linear function. For values close to a, we found that the value of the linearization was a good approximation to the function values of f. For the case of two variables, we can do exactly the same thing. Indeed, the tangent plane is again the graph of a function called the linearization of f at the point a. This linearization is now defined by the property that it has the same function value at the point a and the value of both of its partial derivatives are the same as the corresponding values of the partial derivatives of the function f at the point a. Since the linearization must be a linear function, this completely fixes the function. Again, the linearization allows us to approximate the function values as long as we stay close to the point a. In this case, it may not be completely clear how we should generalize the linearization to functions of more than two variables. Indeed, the notion of a tangent plane doesn't make much sense, particularly since we cannot visualize the graph of a function of more than two variables. Notions of the graph and tangent spaces to such functions do exist, but we will not consider them here. Instead, let's note that the defining quality of the linearization mentioned above does still make sense. So if we consider a function of more than two variables, we can still consider the unique linear function that has the same function value and the same partial derivatives at that function in a particular point. This leads us to the definition of a linearization as you can see on the slide. For example, consider the function f of 3 variables and the point shown on the slide. The partial derivatives are given as shown on the slide, and so we find the corresponding values of the partial derivatives and the function value at that point of interest. By plugging these in the formula for the linearization, we obtain the linearization of the function f at the given point. Let's also consider how we may use the linearization. For instance, consider the point in three-dimensional space given on the slide. Suppose we would like to know how far away it is from the origin. The formula for the distance to the origin follows from Pythagoras' theorem and is given by the square root of x squared plus y squared plus z squared. However, at a given point it is difficult to consider a decimal expansion of this number. So let us, instead, see if we can get an explicit approximation by using the linearization. Obviously, we must consider the function d given on the slide around some point close to the given one, where we do know the distance to the origin explicitly. The point indicated on the slide will do nicely since it is close to the point we're interested in, and we can compute its distance to the origin exactly. By considering the partial derivatives with respect to each variable and plugging in the point, we find the linearization. So to approximate the distance to the origin, we simply plug in our original point to obtain the explicit approximation given on the slide. Of course, every approximation comes with an error. For a function of a single variable, we learned that we can reduce this error by considering the higher order approximations known as Taylor polynomials. This concept also exists for functions of several variables, and perhaps you can actually see how they would be defined in that case. For this course, however, we will not consider them and be content with the linearization. One thing that we should be a bit careful about is the concept of differentiability. We already saw that one or more partial derivatives can fail to exist for a function of two variables. However, it is even possible for both partial derivatives to exist and the function still to be not generally differentiable. We will mostly concern ourselves with particularly nice functions which are differentiable everywhere, and in fact those functions are very common in practice. As a heuristic definition of differentiability, we can consider that a function of two variables is differentiable at a given point if it looks roughly like its tangent plane at that point. On the slide you can see the graph and formula for a function that is not differentiable at the origin, to indicate the kind of behavior we avoid by only considering differentiable functions. For functions of a single variable, we saw that the linearization also leads to a convenient approximation of only the change in function value caused by a change in the input value. Indeed, this was captured in the concept of a differential. Just as in the single variable case, we can also consider the differential of a function of several variables, and the relationship with the linearization is the same. In particular, suppose we consider some change in input given by a shift of delta x equal to dx for the x-coordinate and delta y equal to dy in the y-coordinate. Then we may approximate the difference delta f in the function value by the differential df, given by the corresponding change in this value of the linearization. This leads to the formula you can see on the slide. A common application of such an approximation is to consider the volume of some kind of container. Indeed, consider a cylindrical can of height h and radius r. Then the can contains a volume given by the height h times the area pi times r squared. Now if we assume the can has a thickness of 0.1, then this corresponds to a small change dh equal to twice 0.1 in the height of the can and a small change of dr equal to 0.1 when going from the inside to the outside of the can. So the volume of metal needed to fabricate the can is given by the formula you can see on the slide. We could compute this exactly, but for this example let's consider the approximation provided by the differential. Indeed, the volume is a function of two variables, which means we obtain the indicated differential. So if we then plug in the relevant values of r, h and the change dr and dh, we find the approximate volume as indicated on the slide. Make sure to practice the topics of this video by doing the exercises under this lesson. Good luck!